So today we're going over matrices, the introduction to matrices. And just know this is not the first time you're seeing matrices. We saw it in Algebra 2. Okay, so hopefully some of this rings a bell, just a little bit. It may not, because we know our brains don't always hold all the information we want them to. But hopefully some of this is seeming familiar. Now, a matrix is a rectangular array of numbers, and matrices, which is the plural, matrices, what the heck, provide an efficient way to solve systems of linear equations. So if you remember from Algebra 2, we taught you ways to solve linear equations, systems of linear equations, by substitution or elimination. Well, when the systems get too big or get bigger than you want to deal with, you can just convert them into a matrix, and it's an easy way to solve. That's why matrices were originally created. They're created to deal with systems of linear equations. Now, by definition, if we let n and m be positive integers, then an m by n matrix, written as like, it kind of looks like m times n, mxn, that's an m by n matrix, is a rectangular array of m horizontal rows and n vertical columns. All that this means is that when you're given the order or size of a matrix, the first number is the number of rows and the second one is the number of columns. That's all that means. Also, this m by n is the order of the matrix or the size of the matrix. All right. So here we have an example of a matrix that is infinitely large. And notice that each position inside of the matrix has a special sub number. Now, each element or entry, or I like to call them positions, can be denoted with this A sub ij, where it's all of this is awful, like it's worded very complexly, but the first subscript number is your row number, and the second subscript number is your column number. So that's the I here. The I is the row, and the J is the column. And a matrix is said to be square when m is equal to n. So let's try applying some of this. Ooh. All right. So first we're finding the order of B. Remember, order is like size. So when we're stating the size or order of the matrix, we list first the number of rows and then the number of columns. So how many rows does this matrix have in number 1? How many rows? 2. So this is a 2 by, how many columns does it have? Yes, so this is a 2 by 3 matrix. Is this matrix square? No, right? It's a 2 by 3. These numbers would have to be the same, and clearly it would have to look more like a square itself to be a square matrix. So now we're getting into term or entry or element values. So it wants to know, what is the value of B11? Now remember that first number is the row and the second number is the column. So what is the value of B11? Row 1, column 1. Yeah, 1, right here. Row 1, column 1 is 1. What about B23? Yes, row 2. Oh, let's not do it like that. This is row 2, this is row 1, this is column 1, column 2, column 3. So row 2, column 3 is 6, is equal to 6. What about lastly B32? What do you guys think? Yes, there is no row 3, so this does not exist. Well, I can abbreviate because I'm lazy. DNE does not exist. All right, so let's practice again. On a new matrix, we want to know what A12, what is the value of A12? That's row 1, column 2. We're looking in our first row, and yes, it's 5. First row, whoops, why did I write B? This is A, first row, second column. And now they want us to do a little bit more complex operations. Now, when doing matrices and when finding values inside of matrices, order of operations applies. So first we're going to find the values of A13 and A21 and multiply them together. So what is A13? What is that value? First row, third column. 1. Good. This is A13. What about A21? 3. Good. Yes, this is A21. And then we can just go ahead and find A11. What's A11? 2. Good. So then we multiply 3 times 1 and get 3. We multiply 2 times 2 and get 4. And then we add them together. 3 plus 4 is 7. Honestly, it's not really normal for them to ask something like this. This is just trying to get you used to identifying positions, getting you used to the notation. There's no like usefulness in this. All right. So now we're going to talk about adding and subtracting matrices, whole matrices. When we are trying to add and subtract matrices, they must be of the same order or the same size. If they're different sizes, we cannot add or subtract them. Now, besides knowing they have to be the same size, adding and subtracting matrices is really straightforward. You just have to add and subtract the numbers in the same positions. So if I'm looking at, in this first set of matrices that we're adding together, if I'm looking at row 1, column 1, I'm going to take that and add it to row 1, column 1 in the second matrix. So 3 plus 0 is 3. If I'm looking at row 1, column 2, I must add that to row 1, column 2. 6 plus -1 is 5. And then I just keep going. -1 plus 6 is 5. -3 plus 0 is -3. -5 plus 2 is -3. And what color have I not used? Orange? -1 plus 3 is 2. And that's all there is to it. Adding and subtracting matrices is super straightforward. There's like some banging going on. I don't know what's happening. Any questions on adding matrices? All right. So now I want you guys to give me these values. We are subtracting. So you kind of think of the subtraction as distributing the subtraction to the second matrix. So what is my row 1, column 1? Yes, because I do -5 minus 6. What is my row 1, column 2? Yes, because we have 2 minus -5, which is 7. What about row 1, column 3? Wonderful. Row 2, column 1. Yes. Row 2, column 2. Yes. And lastly, row 2, column 3. It's a +3 because it's -2. I'm sorry, it's 0 minus -3. So that becomes a +3. All right. Any questions on adding and subtracting here? You guys seem like you get it. Okay, so now we're going to do a little bit more complex. I think I might skip number 5 and just, yeah, I don't think it's really needed. Let's just go over the harder one, number 6. All right, so like I said, order of operations still applies. I disagree. Order of operations still applies to matrices. So in this case, what do you think we should do first here? Multiply times 3, yes. Now I do want to, oh, that's right. Okay, this is the first time we're doing scalar multiplications. Anytime you're multiplying by a scalar, by a number, right? There's a number outside of your matrix. You're just distributing that number to everything inside of your matrix, okay? So here in this case, first, before we do that distribution, we should work inside of the parentheses first. Meaning I should combine the two matrices. Because if I were to immediately distribute that -3, I would technically be double distributing one number. I'd be multiplying by -3 twice, which is not what this is asking us to do. So first I'm going to add the two matrices inside of my parentheses. So I'm going to add 0 plus -6, -3 plus 3, 7 plus 8, and 2 plus 1. Just bringing this down now to make it look nice. Then, I guess maybe I should have done this in different numbers so you know that's what I did. Whoops. All right, then we can go ahead and distribute. So I'm going to distribute the -3 to everything inside of my parentheses. -3 times -6 is 18. -3 times 0 is 0. -3 times 15 is -45. And -3 times 3 is -9. And I'm also going to distribute. Now you can either distribute the -2 or just the 2. I'm just going to distribute the 2 here. Leave the negative in between. And now that we have distributed those scalar multiples, we can subtract these two matrices. Oh, let's not do green. Let's do red, pink. 18 minus 8 is 10. 18 minus negative 8. I'm sorry, 0 minus negative 8 becomes plus 8. Negative 45 minus 14 is negative 59. And negative 9 minus negative 18 is 9. And that's our final answer. So it's just honestly just order of operations. Are there any questions on this one? All right. So now, really quickly, here they're having us solve for variables inside of a matrix. Clearly here we can see we have a single matrix set equal to a scalar times the matrix. So in order to know what those variables are, we need to first distribute the scalar into my matrix. So I'm going to do 2 times 1 and get 2, 2 times 4, 2 times 3, and 2 times 3. So now that I've distributed, what was I trying to draw? I don't know. What do you think z is equal to? Yeah, right? In the same exact position as z is 8. What about r? What do you think r is? 6. Perfect. Pretty straightforward, I hope. Any questions? All right, we're going to skip 8 because your Math Excel doesn't have any word problems, but I do just want to point out, they're saying that the production increased by 20%. What are we going to multiply this matrix by, do you think, in order to show a 20% increase? Yes, 1.2. Because we're increasing by 20%, we need to include the original 100%. So we're going to multiply by 1.2. Good, good, good. All right. So now we start getting into the good stuff, the somewhat more complex stuff. We're going to be multiplying matrices. Now, when we're multiplying matrices, you're multiplying the rows of the first matrix by the columns of the second matrix. Matrix multiplication is not what is called, I always mispronounce this, but commutative. Adding and subtracting matrices was commutative, meaning that we just took the same positions, the same entries, and combined them. That is not how matrix multiplication works. We don't just multiply the same position numbers. That's not what we do. Instead, you multiply the rows of the first times the columns of the second. Now, before we actually do this multiplication, we need to figure out if we can actually multiply the given matrices, because sometimes we can't. You can only multiply matrices when, if we're looking at the orders of the two matrices, the middle two numbers match. So here you see we have two matrice orders, M by R matrix, and an R by N matrix. If the two middle numbers match, that's what tells you you can multiply those matrices. And then the outer two numbers tells you the dimensions of the product. So whatever you're going to end up with once you multiply, the order is determined by these outside numbers. So on these following 4 problems, what we're going to do is we're going to check if we can multiply them, and then we're going to figure out, okay, what is the order of the product? What is the size of the resulting matrix? So I'll do number 9 completely with you. First, we have to figure out, okay, what is the order of both of these matrices? Well, this first matrix has 1 rows and 2 columns, so it is a 1 by 2. The second matrix has 2 rows and 2 columns, so it is a 2 by 2, and we're multiplying these together. Our 2 middle numbers match. So can we multiply this? Yes, because our 2 middle numbers match, we can. And they then want to know what is the size of our product. The size or order of our product matrix is the outside numbers. So this is going to be a 1 by 2. Like that. Number. It's going to be a 1 by 2. Okay, so let's try it again. Here we have a what size matrix. What is our first order that I should write down? Yes, it's a 2 by 1. And what is the order of the second matrix? One by 2. Can I multiply these? Yes, we can, because the middle numbers match. What is the size of our product matrix? Yes, 2 by 2, because those are our outside numbers. Okay. Again, let's just do it. Can we multiply this? Yes, we can. What is the size of our resulting matrix? We'll see if you guys get it right off the bat. 7th didn't. Oh, you did. Good. 7th period was like 3 by 1, 3 by 3, 1 by 3. I'm like, what? This is a 1 by 3. This is a 3 by 1. So our resulting matrix should be, whoops, a 1 by 1. Right? Those outside numbers again. Inside numbers tell us we can. So this is a 1 by 1. All right. Lastly, can we multiply this? No, our middle numbers do not match. So it is not possible. Any questions on this so far? Okay, so when we're multiplying matrices, you should just always in your head be thinking we're multiplying rows of the first times columns of the second. Okay, so like in this example, we'll just go back and look at these. In this example, I only have one row. So I'm multiplying all of row 1 times all of column 1 and adding those two values together because there's two entries in this first row. So if I'm looking at this example here, which is the same as the example 9 that we were just looking at, right? We have a 1 by 2 and a 2 by 2. So we can multiply it, and the resulting will be a 1 by 2. I'm multiplying the rows of the first times the columns of the second. And if there's more than one entry in the row, then you'll add the values together. So I'm multiplying my first row times my first column. And if there are multiple within this, you add them together. So multiply the first entry in the first row times the first entry in the first column. -1 times 5. And add it to the second entry in the first row times the second entry in the first column. 2 times 3. So -1 times 5 is -5 plus 2 times 3, which is 6. We get 1. And what this gave us was our number in the first row, first column of our resulting matrix, 1. This is position C11. So now, because I only multiplied my row times my first column, I now need to do the same to my second column. So I'm first going to multiply the first entry in my first row, times the first entry in my second column. So I have why did I erase when I'm doing it again right below? I'm so sorry. Ugh. Let's try to get the same workings here. There we go. Okay, so now I'm multiplying my row times my second column. So I have -1 times 0. Then I add that to the second entry in my first row times the second entry in my second column, 2 times 2. And then I add those together. -1 times 0 is 0, plus 2 times 2 is 4. 0 plus 4 is 4. So that is the value of my first row, second column, because I multiplied my row times my second column to get that value. I know this may not be making sense yet. It's okay. We're going to do it again. All right. So let's look here. First, we have to determine if we can multiply. So this is a 2 by 1. And this is a 1 by 2. Our middle numbers match, so we can multiply. And our resulting matrix is going to be a 2 by 2. So you could write all of the operations off to the side if you wanted to. I'm just going to write them in the positions where they go immediately, just so I can keep track. You can do it this way if you'd like. This is how I like to do it. So remember, we're multiplying the rows of the first times the columns of the second. So there are 2 rows here. I'm going to be looking at row 1 first only. So I multiply first. I take the first row and I multiply it by the first column, which is -5. So you have 6 times -5. That's what goes in your first position, your first row, first column position. Then we multiply again that same row, which has a value of 6, times the second column. And this is what gives us our first row, second column entry. Notice how I am not doing any adding this time. This is because there are not multiple entries within the rows. Okay, so then I'm going to look at my second row. And I'm going to do the exact same thing. I'm going to multiply my second row's value times my first column. So -3, oh, I should do a different color. -3 times -5. And that is my second row first column value. And then I take my second row and multiply it by my second column. And that's how I get my second row second column value. And then I can actually, oh, I forgot to do a different color again. Whoopsies. Then I can actually multiply these together. And I end up with 6 times -5, -30, 6 times 4, 24, -3 times -5 is 15, and -3 times 4 is 12. -12, sorry, -12. Any questions? Okay. So the reason why I don't want you to sweat too much about this is because you can do matrices in your calculator. Is there most likely a way that you can do them in Desmos? Yes. Do I know how to at this point right now? No, but I'm sure there's a matrix button somewhere on Desmos. But anyway, if we are trying to multiply two matrices together, in order to get a matrix to show up on our calculator, there's two ways to do it. I'm going to show you the easier way. You just press alpha zoom, and it immediately brings you to this little table that's asking you how many rows and how many columns in your matrix. So if I'm trying to input this first matrix, this 2x1, I'm going to put 2 rows, 1 column, and it will immediately give me a 2x1. And I put my values in, and I'm going to multiply this by, I hit alpha zoom again, and this is now a 1/2, and I input -5, 4. And look at that. It gives us the exact same answer. So if I'm trying to do this one, alpha zoom, this is a 1/3. You type it in wrong. If you put, like if you accidentally switch it and put 3/1, obviously it will be vertical instead of horizontal, and you know you did it wrong. Times alpha zoom. This is a 3 by, what happened? Zoom, there we go. This is a 3/1 now. Two, 4, 0. And our resulting matrix is a 1/1, 0. That's it, we're done. If you wanted to know how to do this one by hand, remember we're multiplying the rows of the first times the columns of the second. So in our row, there are 3 entries, meaning this is how I know this time I will be adding, because there are multiple entries within the row. So what I do is I take the row's first entry times the column's first entry negative 2 times 2, and I get negative 4, plus the row's second entry times the column's second entry, the row's third entry times the row's third entry. I'm sorry, column's third entry. And then negative 4 plus 4 is 0. Any questions on this? So obviously me showing you this in the calculator, you could have done all of the addition and subtraction in the calculator as well. So you could have gone back and checked all of this work by just plugging it in your answer. I mean, plugging it into your calculator. All right, we're not going to do 12 because, again, there aren't word problems on your Math Excel. All right, I went over how to use your calculator for multiplying matrices. Let's see, what time is it? 3:33. What time do we get done here? 3:40? Okay, we're doing about the same as the last period on time. All right. So let's go ahead and we're just going to, for a minute, talk about what is called an identity matrix. Now, an identity matrix is just a matrix that is always square. It's an n by n, and it only has ones and zeros, where the ones are on the diagonal. So if we're looking at an identity matrix of size 2, that's going to be a 2 by 2 matrix that has ones on the diagonal and 0 everywhere else. If I'm looking at an identity matrix of size 3, that I sub 3, that's going to be a 3 by 3 with ones on the diagonals and zeros everywhere else. Ooh, I drew this kind of small. I can do it though. There we go. And again, an I sub 4, an identity matrix of size 4, is going to be a 4 by 4. Let me draw this one a little bigger. Ones on the diagonals and zeros everywhere else. And so on. Infinitely big for our identity matrices. Now, if A is some matrix, some n by n matrix, meaning it's a square matrix, and we multiply this matrix by an identity matrix, and we end up with just the A value, just the original A matrix. We call this the multiplicative identity. So when I'm multiplying matrix A times an identity matrix, or I'm multiplying identity matrix times matrix A, all of these should end up equaling the matrix A. This is the multiplicative identity. Basically, it's the exact same thing as saying anything times 1 is itself. Now, if when I'm multiplying two separate matrices, A and B, if I end up with an identity matrix, this means that A and B are inverses of each other. They are inverses. This is the same concept as saying 1/2 times 2 is equal to 1, right? They are inverse numbers of each other. So if I'm multiplying matrix A times matrix B and it ends up equaling an identity matrix, that means B is the inverse of A. And we can write it as B is equal to A to the power of -1. Now, if a square matrix has no inverse, it's called singular. If a square matrix has an inverse, it is called non-singular. Now, there's a simple test to determine if a matrix is going to have an inverse. If, when you're finding something called the determinant, if the determinant is not equal to 0, this means your matrix will have an inverse. So let me write that. Yes, inverse, I'll say. If your determinant is equal to 0, there is no inverse for that matrix. Just a simple test to figure out, okay, is there going to be an inverse or not? Now, when finding the determinant, all you have to do is take the values on your forward-facing diagonal. So like if you're starting in the top left and going to the bottom right, this is what I call the forward-facing diagonal. If you multiply those values together, so A times D, and then you subtract the other diagonal's values multiplied together, so C times B or B times C, this is how you find the determinant. A times D minus B times C. So let's go ahead and in this matrix A, let's find the determinant. So I'm going to do 1 times 4, and I get 4, minus 2 times 3, and I get 6. So my determinant here is -2. So will there be a matrix? I'm sorry, will there be an inverse? Yes, because my determinant is not equal to 0. So yes, there will be an inverse. Now, this is the way that we can by hand find the inverse. You take the determinant, put it under a 1, multiply it by this new matrix, which is switching the A and the D and negating the C and the B. But instead of doing all that, because we now know that we can use our calculators for matrices, it is much easier to just input our matrix into the calculator. 1, 3, 2, 4, and finding the inverse of this just by hitting the inverse button, which is that x to the power of -1. This is our inverse. -2, 1, 3/2, -1/2. Most times they're going to want you to put them as fractions, I believe. Also, if you're confused on how to find the determinant, we can, well, let's do this first. If you hit math, I believe, no. If you hit second, the inverse button, x to the power -1, this is how you can compute things with matrices. So if you hit, again, second matrix, or second x to the power -1, and you go over to math, you see how it says DET? That stands for determinant. We can find the determinant of our matrix this way as well. Or you can do it by hand, either one. Yep, second matrix, which, I mean, it's written in blue above that x -1 button. Yeah. All right. Now, I don't have time for it. There is, it gets harder as the matrices get bigger. It gets harder to find the determinant and therefore the inverse. I'm going to save this for next class. I think there's only 1 or 2 problems on your Math Excel that deal with a bigger matrix like this for inverse and determinant. Either you can figure it out on your own, it works the same way, or you can wait till next class when I'll go over it, okay? But either way, we are done, and I'll see you next Wednesday.